Okay, welcome to lecture 35 in Unit 5, Plane Autonomous Systems. So today we are moving on to nonlinear systems of ODEs, and well, we're still working with plane autonomous systems, so there'll be actually plane nonlinear autonomous systems of ODEs, which means we'll have two equations, each of them depending on the independent variable t, but t doesn't appear explicitly on the right-hand side of the equation. So we're still dealing with autonomous systems, but now we're just moving to nonlinear systems. So we want to identify the critical points of these nonlinear systems. So now for nonlinear systems, there will be more than, well, there'll be potentially have critical points that are not at 0, 0, whereas for linear systems, they were always at 0, 0. And we want to classify the type and stability of these critical points. So let's get into it. This is just a reminder from the last episode, the last class, critical points of linear systems. This was basically the summary slide that we had 5 cases, which the type and the stability of each case, of the critical point in each case, was determined by the eigenvalue or eigenvalues of the coefficient matrix A. Okay, this is for linear homogeneous systems. But now let's consider the plane autonomous system of 2 differential equations where the functions f and y can be nonlinear in x and y. Okay. So if the functions f and g are nonlinear in x and y, then we cannot write this as a linear system of equations in the form x prime equals a times x. Okay, so that's a problem. So we can't write this in this lovely matrix form that we could solve. But we can actually linearize the system around the critical point or points of the system. So in other words, if you remember back to your first year calculus, sometimes we would expand a Taylor series of a function. And if we did that, we got a constant plus something times let's just say times x plus something times x squared, and so on. So if we just stop at that constant plus something times x, then we have a linear equation. Okay, if we just ignore the x squared terms and we say they're small, then we got a linear equation. So that's basically what we're going to do here. So we're going to let x naught be a critical point. So x naught is the point x naught y naught, be a critical point. Okay, so a critical point is where this function f is equal to 0 and at the same time g is equal to 0. These both have to be equal to 0 simultaneously. Okay, if f is equal to 0 but g is not equal to 0, this is not a critical point. They must be 0 simultaneously. So we're going to expand the function f and the function g in a Taylor series near the critical point x naught. So, well, you might like to look back to your notes from first year calculus and how we expand a function in a Taylor series. But we're actually going to, because these functions f and g are functions of 2 variables here, x and y, this Taylor series is going to be an expansion in 2 variables. Okay, so we start out with the function is equal to the value of the function at x naught, y naught. Okay, so that's at the critical point, plus the partial derivative of the function f, so the first function f, with respect to x. This line here means evaluated at x naught, y naught. So if we calculate the value of this partial derivative, and we substitute in the numbers x naught, y naught into that partial derivative. Okay, and then we multiply whatever that is by x minus x naught. So x is the variable, x naught is the point. Okay, so we have some f is equal to some number plus, this is again going to be some number because it's just the partial derivative with these points substituted in, multiplied by the variable x minus some number x naught. So where x naught is the critical point, x naught, y naught is the critical point. Okay, but we also need to add a partial derivative with respect to y. So we have the partial derivative of f with respect to y, again evaluated at the critical point, multiplied by y minus y naught. Okay. Okay, so that's the first two terms in the Taylor series. There are going to be higher order terms, so we're going to write this as plus some higher order terms which are of order x squared and y squared. Okay, so these terms, these higher order terms, these are going to be really small, and I'll show you why shortly. But first, I just want to do the same thing for the function g. So I have the Taylor series for f here, and the Taylor series for g, which of course is very similar, except we're taking the partial derivatives with respect to g and evaluating this function g instead of f. And the key point is that this Taylor series expansion is only valid in a region near the critical point x naught, y naught. So probably in first year, you looked at Taylor series and you calculated the error as you got further away from the point of expansion. And that error grows quite rapidly. So as long as we're in a region close to the critical point, then this Taylor series is fine. Okay. But let's have a think for a minute. X naught, y naught is a critical point of the system, isn't it? So we said x naught, y naught is a critical point of the system. So that means that when I evaluate, by definition of the critical point, when I evaluate the function f at the critical point, I get 0. When I evaluate the function g at the critical point, I get 0. So that means that these two terms, the first two terms in the Taylor series expansion, f of x naught, y naught, and g of x naught, y naught, these are 0. So these two terms here are 0, just because we are at a critical point. Okay, and then the second point is that we can ignore the terms of higher order, so the x squared and y squared terms, and this is because near the critical point, x minus x naught and y minus y naught are small. Okay, so if we're in a region where x is close to x naught and y is close to y naught, then this difference, x minus x naught and y minus y naught, they're both very small. So therefore, x minus x naught squared and y minus y naught squared are very small. So approximately 0, we're going to say they're close enough to 0 that we can just throw them out. Okay. So really all we get left with, by the time we've thrown out these higher order terms in green here, and the fact that f evaluated at the critical point and g evaluated at the critical point are both equal to 0, all we're left with is the Taylor expansion of f, or the linearization of f, is just the sum of these partial derivative with respect to x times x minus x naught, the partial derivative of f with respect to y times y minus y naught, and similar for g. And again, remember these partial derivatives are evaluated at the critical point. So now we can write this as a linear system. Okay, so we can write x prime, which is still the left-hand side of this system here, is equal to a times x minus x naught, where x minus x naught is this x minus x naught here, y minus y naught, x minus x naught, y minus y naught. And the a here, this matrix A is going to consist of these partial derivatives evaluated at critical points. Okay, so df by dx, df by dy, dg by dx, and dg by dy. Okay. So I've just expanded that here. A is equal to this matrix of partial derivatives evaluated at the critical point, x naught and y naught. And we call A the Jacobian matrix at the critical point x naught. So this is a really important matrix that comes up a lot in dynamical systems, the Jacobian matrix. Again, just pointing out that these partial derivatives are all evaluated at the critical point x naught. All right, so now if we actually we define a new vector h, which is x minus x naught, so the dependent variable minus the critical point, I can take the partial derivative of h here. Well, that would just be x prime, right? Because if I take the partial derivative of the left side, I get h prime equals x prime minus, well, this is a constant matrix. This is our critical point, so this is 0. If I take the derivative of a constant matrix, I get 0. So I can actually write this linear system 1 here as h prime, which is equal to x prime, equals a times h. So the critical point x naught for the system 1 here corresponds to the critical point h equals 0, or the origin for the second system over here. What that means is we've already analyzed the nature of critical points of these linear systems, right? So systems that look like equation 2 here. So it turns out that the nature of the critical point, that is whether it's a node, a spiral, a saddle point, or a center, and so on, we've already learned how to do that. Okay, so by nature I mean, yeah, the classification as a spiral, a node, anything like that. But we haven't actually, you can't use the same stability criteria as for linear systems. Okay. So, well, let's get into what I mean by that. So this is the slide for the critical point of linear systems. Okay, so again, really highly recommended that you print this out. For nonlinear systems though, well, the cases all are equivalent in terms of the nature. So case 1 is still a node for a nonlinear system. Case 2 is a node for a nonlinear system. Case 3 is a saddle point. Case 4 is a spiral. Case 5 is a center. But we just don't know the stability yet of this nonlinear system. So, okay, so let's write down some theory about nonlinear system stability. So we're going to let x naught be a critical point of this system of nonlinear autonomous differential equations. If f and g have to have continuous first order partial derivatives close by the critical point, okay, otherwise we couldn't calculate those derivatives. So the first point here is that if the eigenvalues of the matrix A, that Jacobian matrix A, have negative real parts, then x naught is a stable critical point. Okay, so again, this is very kind of similar to the linear case, is that if our eigenvalues had negative real parts, then we had a stable critical point. But also, if A has an eigenvalue with a positive real part, then the critical point is unstable. And again, that's fairly similar to the linear system case. So let's create a summary slide for our nonlinear systems. So it's going to be 3 points here. For each of the cases of stable and unstable nodes, so case 1 in linear system, unstable saddle point, so case 3 in linear system, and stable and unstable spiral point, or case 4 for linear systems. So in the small neighborhood of the critical point, because our Taylor series is only valid in a small neighborhood of the critical point of the nonlinear system, the solutions have the same geometric features as the solutions of the linear systems. So for the case of stable and unstable nodes, unstable saddle points, and stable and unstable spiral points, linear and nonlinear systems, the conclusions are exactly the same. Okay. However, for the case of repeated eigenvalues, so this is case 2 for linear systems, so lambda 1 equals lambda 2, if lambda 1 equals lambda 2 is greater than 0, so if the eigenvalues are positive, then the critical point is unstable. But it may either be an unstable node or an unstable spiral point. We can classify that it's unstable, but we can't say whether it's an unstable node or an unstable spiral point. Okay, so we just don't have enough information. Basically, the reason we can't determine between those two cases is because we lose a little bit of information due to the Taylor expansion, the fact that we were throwing away those higher order terms. Okay, so we lose a little bit of information there. If the eigenvalues, the repeated eigenvalues, are less than 0, then the critical point is stable, but it could be either a stable node or a stable spiral point. And again, for the same reason, we just lose a little bit of information by throwing away those higher order terms. So that linearization allows us to classify the critical point, but we can't fully classify it. Okay, case 3, if we have complex conjugate eigenvalues, which are pure imaginary, which is case 5 for linear systems. So in the linear system, that was a center. But for the nonlinear system, the critical point could either be a stable or an unstable spiral or a center. Okay, so it's not possible to tell whether the critical point is stable or unstable. And the reason for that is because if you recall, in these centers, the real part of the eigenvalue was 0, of course. But if we throw away the higher order terms, then we might be throwing away a very small positive real part or a very small negative real part, and that could obviously, if we're saying here that it's exactly 0, but we could be a little bit wrong because we are throwing away those higher order terms, so we're losing that information. Okay, so there is going to be a summary at the end of this lecture, so hang in with me, please. Let's look at a few examples though. So we have the nonlinear system here, x prime equals 2x minus y squared, so clearly nonlinear, y squared. Y prime equals negative y plus x times y, so clearly nonlinear, x times y. And we're asked to classify the critical points of this nonlinear system. Okay, well, if we're going to classify the critical points, we better know where the critical points are. Okay, so first we're going to find the critical points. So remember, the critical points are where each of the functions on the right-hand side are equal to 0 simultaneously. So 2x minus y squared equals 0, minus y plus xy equals 0. They both have to be 0 at the same time. Okay, so the first equation tells us we could rearrange that to say that x is equal to y squared over 2. And then we can use that in the second equation. So minus y plus y squared over 2 times y equals 0. Okay, well, I seem to have... Okay, so sorry, here I've... before I did that, I rearranged this equation. I took out the common factor of y. So I have negative y times 1 minus x equals 0. So I guess I was focusing on this one first. From 2, well, clearly y equals 0 would set this equation equal to 0. X equals 1 would set this equation equal to 0. And from this equation 1 here, if y equals 0, then x must equal 0 as well. So if y equals 0, this case here, then x equals 0 squared over 2, which is 0. So 0, 0 is a critical point of the system. However, if x equals 1, so to make this equation here 0, equation 2, if x equals 1, from the first equation we have 1 equals y squared over 2, or y squared equals 1 times 2, or y is equal to the square root plus or minus the square root of 2. So we actually have 3 critical points here. We have the critical point 0, 0, and the critical point x equals 1, y equals square root 2, and the critical point x equals 1, y equals negative square root 2. Okay, so we've got these 3 critical points that we've found now. Of course, the next part of the problem is to classify these 3 critical points that we've found. Okay, and so of course to do that we need to calculate the Jacobian matrix. And recall the Jacobian matrix was just the partial derivative of the right-hand sides of the equation. Okay, so let's do this now. So, well, the first term here, df by dx is, well, here's the f is 2x minus y squared. If I take the partial derivative of that with respect to x, then I'm going to get 2. Okay, if I take the partial derivative of the first equation with respect to y, I'm going to get minus 2y. If I take the partial derivative of the second equation, g, with respect to x, I'm just going to get y. And then finally, the last term was going to be x minus 1, or minus 1 plus x. Okay, but recall, so that's the matrix of the partial derivatives. But recall, I have to evaluate these partial derivatives at the critical points. So I've got to evaluate this matrix A at these individually at each of these 3 critical points. So here's my matrix A. Now I have to evaluate it. Let's start with the point 0, 0. So if x equals 0, y equals 0, then we have 2, 0, 0, negative 1. Okay, well, this is a triangular matrix, so I can already just read the eigenvalues off the diagonal. I have lambda 1 equals 2, lambda 2 equals negative 1. Well, in that case, I'm going to have an unstable saddle point. Okay, an unstable saddle point. So that was an easy one. For the critical point 1 square root 2, if I substitute that into the matrix A, then this is the matrix I get. So now I need to calculate the eigenvalues of this matrix. Well, again, I can do that as the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. Okay, and what do I get when I do that? Well, I actually get complex conjugate eigenvalues, where the real part is 1 and the imaginary part is square root 3. Okay, and again, this is a spiral point, which is stable if alpha is less than 0 and unstable if alpha is greater than 0. And in our case, alpha, or the real part, is 1, so we have an unstable spiral point. The third point, we can go through that again rather quickly. We substitute in for x 1 for y negative square root 2 into our Jacobian matrix, and actually we get the same eigenvalues there as well. So in fact, x3 is also an unstable spiral point. So we have 3 critical points to this system. We found x1, the critical point at x1, the origin, is unstable saddle point. The other 2 are unstable spiral points. So of course that was coming from the fact that for stable and unstable nodes, unstable saddle points, and stable and unstable spiral points, nonlinear systems, the eigenvalues of that nonlinear system of the Jacobian give you the same results as for the linear system. But now we should look into some of the other 2 cases. Okay, so let's see what we've got. So classify the critical points of the nonlinear system here. So again, first find the critical points. So we have to set each of these equations equal to 0. So x squared minus y squared minus 1 equals 0, and 2 times y equals 0. So, well, okay, so the only way you can satisfy the second equation is y equals 0, of course. And if y equals 0, then we basically are going to have x squared minus 1 equals 0, or x is equal to plus or minus 1. So we get 2 critical points, 1, 0, and negative 1, 0. So x equals 1 or 1, y equals 0, and x equals negative 1, y equals 0. Notice here that the origin is not a critical point. Okay. Because even though the second equation is 0 when y equals 0, the first equation is not. It would be equal to negative 1 at the origin. So it's not a critical point. So we have 2 critical points. We can calculate the Jacobian matrix fairly easily. So again, df by dx is going to be 2x. df by dy is going to be negative 2y. dg, the second equation, by dx is 0 because there's no x's. dg by dy is just 2. And so now we just need to evaluate this Jacobian matrix at the critical points. So starting off with x equals 1, y equals 0, so x1. The Jacobian matrix, if I substitute in x equals 1, y equals 0, I get this matrix here, which of course you can see is going to have a repeated eigenvalue, which is equal to 2. Okay, so when lambda 1 equals lambda 2, so case 2 for linear systems, if lambda 1 equals lambda 2 is greater than 0, so that's what we have here because we had the eigenvalue 2, then the critical point is unstable, but we don't know if it's an unstable node or an unstable spiral point. So the critical point x1 equals 1, 0 is unstable, but we're unable to classify any further. It could be a node or a spiral point. Okay, well again, now if we go back to the other critical point, x equals negative 1, y equals 0, this is the Jacobian matrix. When I substitute in x equals 1, y equals, x equals negative 1, y equals 0. And so here, of course, I have distinct real eigenvalues. And so I already know that x2, negative 1, 0, is an unstable saddle point because I had eigenvalues, distinct real eigenvalues of opposite sign. Okay, let's do one more example before the end of the lecture. So we have another nonlinear system here. Again, let's find the critical points. So 2 times x times y equals 0, or just x times y equals 0. Y minus x plus x times y minus y cubed equals 0. There's a lot of variables going on there. So the first equation implies that either x is 0 or y is 0. Okay, well, if x equals 0, we could put that into x equals 0 into the second equation here, and then we would have y minus y cubed equals 0. And so y minus y cubed equals 0 is going to have 3 solutions. Obviously, y equals 0 satisfies that equation, or y equals plus or minus 1 will satisfy that equation. So we get 3 critical points, which I'll put up in the top corner there. Okay, but what about, so that was for, those 3 critical points were for y equals 0, for x equals 0. But now if y equals 0 automatically gives x equals 0, right? Because if y equals 0, then we get 0 minus x plus 0 minus 0 equals 0. So we already get that critical point. We already have that critical point 0, 0. So in fact, we only have 3 critical points. We can calculate the Jacobian matrix of this system. So this first equation, if I take the partial derivative with respect to x, I get negative 2y. If I calculate it with respect to y, I get negative 2x. If I calculate the second equation, the partial derivatives, then I get, well, with respect to x, I get minus 1 plus y. And with respect to y, I get 1 minus 0 plus x minus 3y squared. Okay, and so now I need to evaluate this Jacobian matrix at these 3 critical points. So at the point 0, 0, x equals 0, y equals 0, I get the Jacobian matrix like so. Okay, so this is a problem, right? Because it's lower triangular, this matrix. So my eigenvalues are 1 and 0. Well, if I have a 0 eigenvalue, that means that my determinant is equal to 0, and so my whole premise fails. Okay, the test completely fails if the determinant of A equals 0. If one of your eigenvalues is 0, we just cannot classify a point if it has 0 eigenvalue. Okay, x2 equals 0, 1. So, well, you can go through it and show that this is stable and either a stable node or a stable spiral point. X3 is an unstable saddle point, so there we've got some real distinct eigenvalues of opposite signs. Okay, but the last thing I wanted to point out is that there is some useful information on the stream site. If you go under the final exam subheading and download the PDF that's in there, we have 2 pages that I think I would like you to print out and perhaps know, or at least have next to you when you're doing your assignment or test. The first is the stability of linear systems table. So again, if we calculate the eigenvalues of that coefficient matrix A, this has all the possibilities. It tells us the type of equilibrium point, and it tells us the stability of the equilibrium point. So, for example, if we have real eigenvalues of opposite sign, we have an unstable saddle point. Or if we have pure imaginary eigenvalues, then we have a stable center. Okay, so that was for linear systems, but also in that useful table of information is the stability table for nonlinear systems. Okay, so for example, if I have 2 real eigenvalues which are equal, so a multiplicity 1, which are negative, I have an asymptotically stable node or a spiral point. So I can tell the stability, but I can't tell the type of equilibrium point or critical point. If I have a pure imaginary eigenvalues, so the eigenvalues for the nonlinear systems are the eigenvalues of the Jacobian matrix. Yeah, maybe I can make that a little bit clearer. For the linear systems, the eigenvalues are the eigenvalues of the coefficient matrix. For the nonlinear systems, the eigenvalues are the eigenvalues of the Jacobian. Okay, so just a subtle difference there, but important one. Okay. So, well, yeah, if we got a pure imaginary in that case, in the nonlinear case, then we have an indeterminate stability. It could be a center or a spiral point, and it could be stable or unstable. So these two tables, please get to know them really well, and yeah, you'll definitely need them and find them useful for tests and assignments. Okay, so tomorrow or the next class, we're going to go through an example of, well, a practical example of solving systems of differential equations to do with predator-prey models. So the dynamics of if you have one type of animal that's a predator and eating some other kind of animal, which is the prey. I'll see you there.